The morning of September 8, 1944, Staff Sergeant William Mackenzie stood in the vehicle assembly area of the 2nd Armoured Division's Ordnance Maintenance Battalion, watching what should have been impossible. A Sherman tank, its entire Ford GAA 5.8 engine assembly dangling from a makeshift crane, was being lowered back into its engine compartment. The crew had pulled it, diagnosed a cracked cylinder head, fabricated a replacement part, and were reinstalling the whole power plant. Total elapsed time from the moment they'd backed the tank into the maintenance bay, 7 hours and 43 minutes. 3 months earlier, that same operation would have taken 48 hours minimum, often longer. Mackenzie hadn't invented some revolutionary new tool. He hadn't received secret engineering blueprints from Ford's River Rouge plant. What he'd done was figure out that the Army's technical manual for Sherman engine removal, written by engineers who'd never field-stripped a tank under artillery fire, was fundamentally wrong about how mechanics actually worked. And in the process of proving it, he'd accidentally solved a problem that was crippling Allied armoured operations across Normandy. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The problem announced itself with brutal mathematics in July 1944. First Army's after-action reports from the Normandy bocage fighting made for grim reading at 12th Army Group headquarters. Armoured divisions were reporting operational readiness rates below 60%, not from combat losses, from maintenance backlogs. For every Sherman knocked out by German anti-tank guns, 2 more sat immobilized in rear area maintenance depots, waiting for engine repairs that took days to complete. The Sherman tank was supposed to be America's answer to German armoured superiority. Easy to produce, easy to maintain, easy to repair in the field. That was the promise. Chrysler's tank arsenal and Fisher body had cranked out nearly 50,000 of them between 1942 and 1945. But by summer of 1944, that promise of easy maintenance was colliding with the reality of sustained combat operations in Europe. General George Patton's Third Army was burning through Shermans at a rate that would have been unsustainable, if not for one critical advantage. The American military-industrial complex could replace destroyed tanks faster than the Germans could knock them out. But what nobody had adequately planned for was the sheer volume of mechanical failures that came with pushing these machines beyond their design limits. The Ford GAA engine that powered the M4A3 Sherman variant was, on paper, a magnificent piece of engineering, 500 horsepower from a 450 cubic inch aluminum V8. It was derived from a tank version of a V12 aircraft engine with 1/3 of the cylinders removed. The engine itself was reliable, almost too reliable. Crews pushed them hard, confident they could take the abuse. And they could, right up until something failed. Then the question became, how fast can you fix it? Technical Manual 9-731 specified the procedure for complete engine removal and replacement. The manual was written by automotive engineers at Army Ordnance, men who understood engines intimately, but who'd never worked on a tank in a muddy field in France while German artillery bracketed your position. Their procedure called for a methodical, step-by-step process that required removing dozens of components in a specific sequence. First, drain all fluids, engine oil, coolant, fuel, then disconnect the electrical systems, battery cables, starter wiring, instruments. Next came the control linkages, throttle, clutch, brake connections. The exhaust system had to be unbolted. The transmission had to be partially disassembled. The engine mounts required careful attention because they were under tension from the engine's weight. The manual specified that 2 mechanics, working with proper tools and equipment, could complete the removal in approximately 24 hours. That was the theory. In practice, field conditions made the manual's timeline laughably optimistic. Real Sherman maintenance happened in assembly areas 5 to 10 miles behind the front lines. There were no factory-clean workshop floors. There was mud, usually, or dust, if you were lucky. There were no climate-controlled buildings. You worked in whatever weather Northern Europe threw at you. Rain, cold, the occasional summer heat that turned the inside of a Sherman's engine compartment into an oven. The tools specified in the manual assumed you had everything you needed, perfectly organized, within arm's reach. Reality was different. Ordnance maintenance companies were mobile units designed to move with the army. Their toolkits were comprehensive, but not infinite. Specialty tools broke or went missing. Mechanics improvised constantly, using wrenches that were almost the right size, persuading frozen bolts with penetrating oil and profanity, making do with whatever they had. And then there was the human factor the manual writers never adequately addressed. These weren't factory technicians working an 8-hour shift with a lunch break. These were soldiers, many of them draftees, working 12 to 16-hour days, falling asleep on their feet, doing maintenance under blackout conditions with hooded flashlights when German aircraft might be overhead. By mid-August 1944, the 2nd Armored Division's maintenance backlog had reached crisis proportions. The division's 3 tank battalions had a combined authorized strength of 232 medium tanks. On August 15th, only 147 were operationally ready. Of the 85 non-operational tanks, 63 were awaiting engine repairs or major powertrain maintenance. Colonel Ernest Harmon, commanding the 2nd Armored, called a conference with his maintenance officer, Lieutenant Colonel Robert McKee, on August 16th. The conversation, recorded in McKee's personal journal, was blunt. Harmon wanted to know why it took 2 days to change an engine when the Germans were probably swapping theirs in half that time. McKee had no good answer except that they were following the technical manual's procedures. Harmon's response was succinct. "I don't care about the manual. I care about getting tanks back in the fight. Find me someone who can fix this." Staff Sergeant William Mackenzie wasn't the obvious choice. At 31 years old, he was older than most enlisted men, with a mechanical background that was more practical than theoretical. Before Pearl Harbor, he'd run a small automotive repair shop in rural Pennsylvania. When he enlisted in 1942, the Army looked at his civilian occupation and sent him to ordnance school. He'd been with the 2nd Armored's Maintenance Battalion since its deployment to England in late 1943. What made Mackenzie different wasn't his technical knowledge. Half the mechanics in the battalion had similar backgrounds. What set him apart was his obsessive attention to wasted motion. He'd spent 9 years running his own shop, where every minute of labor time translated directly into profit or loss. He understood, viscerally, that efficiency wasn't about working faster. It was about eliminating unnecessary work. The standard engine removal procedure, as specified in TM 9731, required mechanics to work from multiple angles. Some steps required access from the top of the tank, through the engine deck hatches. Others required crawling underneath the hull. Still others required reaching in from the sides, through narrow gaps between the transmission housing and the hull interior. Every time a mechanic changed position, climbing on top of the tank, then underneath, then back on top, time bled away. Mackenzie started documenting actual engine removal times in early August. He didn't tell anyone he was doing it. He just kept a pocket notebook and recorded every step of the process as the battalion's maintenance crews worked through their backlog. What he found confirmed his suspicions. The technical manual's 24-hour estimate assumed perfect conditions. In reality, under field conditions, engine removals were taking between 40 and 56 hours. The problem wasn't the mechanic's skill, it was the procedure itself. The manual's sequence of operations forced constant repositioning. Disconnect the electrical system from the top requires climbing onto the tank with tools. Unbolt the transmission linkage from underneath requires jacking the tank and crawling under it. Remove the exhaust system from the side requires lying on the ground next to the hull. Every position change cost time. Mackenzie realized something that seems obvious in retrospect, but that nobody had formally recognized. The Sherman's engine compartment was accessible from exactly one direction that gave you clear line-of-sight access to almost every critical connection point. From directly behind the tank, with the rear hull plate removed. But the technical manual barely mentioned working from the rear because the engineers who wrote it were thinking about minimizing the number of components you had to remove. They didn't want you taking off the entire rear hull plate because that added steps. But what if those steps saved more time than they cost? On August 23rd, Mackenzie approached Colonel McKee with a proposal. Let him try a different sequence. Instead of following the manual's procedure, start by removing the rear hull plate first. That gave you direct access to the engine from behind. Then, work forward, removing components in the reverse order from what the manual specified. McKee, desperate for any improvement, gave him one tank and told him to document everything. The test began at 0600 hours on August 24, 1944. The subject was an M4A3 Sherman, Bureau number 87432, that had thrown a rod through its engine block 3 days earlier. Mackenzie assembled a crew of 4 mechanics, all experienced men who knew the standard procedure by heart. He walked them through his proposed sequence before they started. Step 1. Remove the rear hull plate entirely. This required unbolting 28 bolts around the plate's perimeter. The manual treated this as an emergency-only procedure because it was time-consuming. Mackenzie timed it. With 4 men working simultaneously, removing and setting aside the rear plate took 47 minutes, but once that plate was off, everything changed. The entire back of the engine was exposed. You could see the transmission connection, the exhaust, mounting points, the engine mounts, the fuel lines, the electrical harnesses. Everything was visible and accessible from a single working position. Step 2. Disconnect everything while standing at the rear of the tank. No more climbing on top, no more crawling underneath. 2 mechanics could work simultaneously, one on each side of the engine, with clear access to every bolt they needed to turn. The electrical system, which the manual said required working from the top with difficulty, was completely accessible from the rear. Disconnection time: 19 minutes. The transmission linkage, which the manual specified required working from underneath, was right there at waist height, easily accessible. Disconnection time: 22 minutes. The fuel lines, same story, 14 minutes. The exhaust system, which normally required lying on the ground and reaching up into a cramped space, unbolted directly from the rear, 28 minutes. By noon, 4.5 hours into the operation, they had the engine completely disconnected and ready to lift. The actual lift procedure was identical to the manual's specification. Attach the crane, take up the slack, unbolt the engine mounts, lift straight up. That took another 45 minutes, working carefully to avoid damaging the firewall or transmission housing. The engine came out at 12:45. Total elapsed time, 6 hours and 45 minutes. The crew stood there, looking at each other, trying to process what had just happened. They'd cut the engine removal time in half, and they'd done it without any special tools, without any modifications to the tank, without anything except a different sequence of operations. But Mackenzie wasn't satisfied with just removal time. The real test was reinstallation. Could they put an engine back in using the same rear access method? Because if you could remove and reinstall an engine in under 16 hours, you could turn around a tank in a single day instead of 3. That would fundamentally change the maintenance calculus. The test continued on August 25th. They had a replacement engine, a remanufactured unit from the depot at Valognes. The standard reinstallation procedure in TM 9731 called for reversing the removal process. Lower the engine, reconnect everything from multiple positions, button it up. The manual estimated 24 hours for reinstallation because everything had to be precisely aligned and properly torqued. Mackenzie's sequence, working from the rear, cut that time to 8 hours and 12 minutes. The alignment was actually easier because you could see what you were doing. The engine mounts lined up cleanly. The transmission shaft engaged smoothly. Every connection was visible and accessible. No more working blind, reaching into cramped spaces with a wrench, trying to thread a bolt you couldn't see. When they fired up that Sherman at 1600 hours on August 25th, it had been out of commission for exactly 49 hours, from the moment they'd backed it into the maintenance bay until engine start. Under the old procedure, that tank would have been down for at least 4 days, probably 5. Colonel McKee watched the demonstration and immediately grasped the implications. If this procedure could be standardized across the maintenance battalion, they could effectively double their engine repair capacity without adding more personnel or equipment. But he also understood that you don't just throw out an official technical manual because one sergeant had a better idea. The army didn't work that way. McKee's solution was pragmatic. He ordered Mackenzie to train every engine mechanic in the battalion on the new procedure over the next 2 weeks. Simultaneously, he documented everything in a detailed report sent up the chain to 12th Army Group Ordnance. The report was carefully worded. It didn't criticize the existing technical manual. It simply presented comparative data. Old procedure, average engine removal and reinstallation time, 48 hours. New procedure, average time, 14 hours. Reduction in maintenance time, 70%. The numbers were impossible to ignore. By mid-September, every armoured division in 1st and 3rd Armies had received copies of McKee's report. Ordnance officers started quietly training their mechanics on the rear access method. Nobody officially changed the technical manual. That would have required approval from Army Ordnance in Washington, a process that could take months. Instead, it spread through the informal network that makes any military organization actually function. A maintenance officer in the 4th Armored Division would mention it to his counterpart in the 6th Armored Division. That officer would try it, see the results, and pass it along to the 9th Armored. By October 1944, the modification had become standard practice in every American armored unit in the European theater. Not because anyone ordered it, but because it worked. The impact on operational readiness rates was dramatic and immediate. 2nd Armored Division's operational readiness for medium tanks went from 63% in mid-August to 87% by October 1st. That meant more tanks available for combat operations, which meant more firepower on the front lines, which meant missions that would have been impossible with half the division's Shermans in maintenance bays waiting for engines. The German army never figured out what had changed. Luftwaffe reconnaissance flights over American rear areas in September and October continued reporting the same concentrations of disabled tanks in maintenance areas. But those tanks weren't disabled anymore. They were cycling through repairs at 3 times the previous rate. What looked like a maintenance backlog to German intelligence was actually a functioning maintenance system, processing vehicles faster than the Germans thought possible. The contrast with German tank maintenance was stark, and would only become more so as the war progressed. German heavy tanks, the Panthers and Tigers that were technically superior to Shermans in firepower and armour, had one critical vulnerability. Their engines were mounted in line, running the length of the hull. Removing a Maybach V12 from a Panther required specialized gantries and cranes. The entire rear hull had to be unbolted. The turret had to be removed first. Even under ideal conditions at a depot-level maintenance facility, a Panther engine swap took 3 to 4 days. In the field, it was often impossible. Disabled Panthers were frequently abandoned because the maintenance infrastructure to repair them didn't exist at the front. German maintenance doctrine assumed that seriously damaged tanks would be transported back to Germany for depot-level overhaul. As the Allies advanced and German logistics deteriorated, that system broke down completely. American maintenance doctrine was fundamentally different. The Sherman was designed from the beginning for field maintenance. Its engine could be replaced forward of the core maintenance area, sometimes even at battalion level if the situation demanded it. The rear access modification that Mackenzie developed made that capability even more effective. But the true test of the innovation came during the Battle of the Bulge, Germany's last major offensive in the West, which began on December 16, 1944. The early morning artillery barrage that announced the German attack caught American forces completely by surprise. Over 200,000 German troops and nearly 1,000 tanks, Panthers, Tigers, and Panzer IVs came crashing through the thinly held Ardennes sector. The attack targeted 4 inexperienced and battle-worn American divisions that had been stationed in the quiet sector for rest and recuperation. Within hours, German spearheads had broken through the American front, creating a massive bulge in the Allied lines. 3rd Army, positioned 140 miles south of the breakthrough near Bastogne, received orders from Supreme Allied Commander General Dwight Eisenhower on December 19. Patton was to disengage from his operations in Lorraine, pivot his entire army 90 degrees north, and counterattack into the German flank. The logistical challenge was staggering. Patton needed to move 3 entire divisions, with all their supporting elements, over icy roads in the middle of winter, and be ready to attack by December 22. The timing couldn't have been worse for Third Army's maintenance situation. 5 months of continuous combat operations from Normandy through Lorraine had worn the Shermans down. Combat Command A of the 4th Armoured Division reported that 42% of their medium tanks required significant maintenance. Some needed track replacement, others had worn-out suspension components, and dozens needed engine work, the kind of engine work that, 3 months earlier, would have taken days per vehicle. But Mackenzie's rear access modification had fundamentally changed the maintenance equation. When the 4th Armoured Division pulled back to assembly areas near Arlon on December 20th to prepare for the attack north, their maintenance crews had exactly 48 hours to get as many tanks combat-ready as possible. Under the old procedures, they might have completed engine work on 8 to 10 tanks. Using the new method, they processed 23. The difference between those numbers meant the difference between having enough armoured striking power to break through to Bastogne or failing in the attempt. Every additional tank that could be made operational increased the odds that the surrounded 101st Airborne Division would survive. The Germans knew this too. They were racing against time, trying to crush the Bastogne garrison before relief could arrive. 4th Armoured Division attacked north on the morning of December 22nd, with Combat Command A taking the main Arlon-Bastogne road. The weather was brutal. Freezing rain had turned the roads into skating rinks. Tank drivers struggled to maintain control on downhill sections, and the icy conditions meant that recovery of any disabled vehicle was nearly impossible. If a Sherman threw a track or suffered mechanical failure during the advance, it would have to be abandoned until conditions improved. The fighting was savage. German forces defending the approaches to Bastogne knew exactly what the Americans were trying to do and fought with desperate intensity. 4th Armoured's advance measured in hundreds of yards per day, not miles. Villages became killing grounds. German anti-tank guns and Panzerfaust teams turned every crossroads into a battlefield. By December 24th, Combat Command A had advanced only 12 miles in 3 days of continuous fighting. They were still over 10 miles from Bastogne, and the weather had turned even worse. Heavy snow reduced visibility to near zero. The temperature dropped to 10 degrees Fahrenheit. Under these conditions, engine maintenance became critical not just for combat readiness but for basic survival. Shermans that couldn't keep their engines running risked having their crews freeze. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The breakthrough came on December 26th. Lieutenant Colonel Creighton Abrams, commanding the 37th Tank Battalion, led a column of 5 Shermans through the village of Assenois in a desperate final push. His lead tank was a Sherman Jumbo, the M4A3E2 assault variant, with extra armour, nicknamed Cobra King. The German defenders fought to the last moment, but Abrams' tanks crashed through and at 1650 hours made contact with elements of the 101st Airborne's 326th Airborne Engineer Battalion. Bastogne had been relieved. But the battle was far from over. The Germans immediately began counter-attacking, trying to cut the narrow corridor 4th Armoured had created. For the next 3 weeks, the fighting around Bastogne would be more intense than the initial siege. German forces threw everything they had at the American positions, including Tiger II heavy tanks from Heavy Tank Battalion 506. The maintenance situation became critical. Tanks were taking battle damage at unprecedented rates. Track links were being shot away, road wheels were being destroyed, and engines were being pushed to their absolute limits in the sub-zero temperatures. The rear area maintenance facilities were processing damaged vehicles as fast as they could get them back to the assembly areas. One incident captured in 2nd Armored Division maintenance logs from January 2nd, 1945, illustrated the system's effectiveness. An M4A3 from Company B, 66th Armored Regiment, took a hit from a German 75mm gun that punched through the engine deck and destroyed 2 cylinders. The tank made it back to friendly lines under its own power, barely, with the engine running on 6 cylinders and pouring oil smoke. Under standard procedures, that tank would have required at least 40 hours of work. Remove the engine, transport it to a depot-level facility for rebuild or replacement. Wait for a replacement engine to become available. Install it, test it. The tank would have been out of action for at least 5 days, probably longer given the backlog of battle damage needing attention. Instead, using Mackenzie's method, a maintenance crew pulled the engine in 8 hours, installed a remanufactured replacement in another 7 hours, and had the tank back in the company motor pool 36 hours after it had been hit. The difference wasn't academic. That tank participated in Combat Command A's attack to clear German forces from the Harlange pocket on January 8th, an operation that required every available Sherman. The cumulative effect of these maintenance improvements across Third Army was substantial. Between December 22, 1944, and January 19, 1945, Third Army's armoured divisions lost approximately 330 medium tanks to all causes, combat and mechanical. During the same period, Ordnance Maintenance units returned 412 tanks to combat-ready status. The operational readiness rate for medium tanks, which had dipped below 70% during the initial German attack, climbed back to 83% by mid-January. The Germans never achieved that kind of maintenance throughput. A Panther or Tiger that suffered major engine damage was, for practical purposes, lost. German maintenance doctrine required that seriously damaged tanks be transported back to Germany for depot-level overhaul. But by December 1944, Allied air superiority made rail transport suicidally dangerous. Hundreds of German armoured vehicles were abandoned in the Ardennes, not because they'd been destroyed in combat, but because they couldn't be repaired in the field. The contrast wasn't lost on German tank commanders. Post-war interrogations of captured Panzer officers repeatedly mentioned American maintenance capabilities with a mixture of respect and frustration. One Tiger Company commander from the 2nd SS Panzer Division stated that American tanks seemed to multiply during battles. His unit would knock out 8 or 10 Shermans in a day's fighting, only to face what appeared to be the same number of tanks the next morning. He wasn't imagining it. American maintenance crews were recovering damaged Shermans, repairing them overnight, and getting them back into the fight with a speed that German forces couldn't match. The Tiger commander attributed this to American industrial capacity, an unlimited supply of replacement tanks. He was partially right about the industrial capacity, but he completely missed the real advantage. American mechanics had figured out how to fix tanks faster than German mechanics could, and that operational advantage was worth divisions. The Battle of the Bulge effectively destroyed the German armoured force in the West. By February 5, 1945, the Germans had only 190 operational tanks on the entire Western Front, facing 10 times that number of American and British armoured vehicles. The numerical disparity would only grow larger as the Allies pushed toward Germany. American maintenance advantages became even more pronounced during the final months of the war. The Rhine crossings in March 1945 required massive concentrations of armour. Third Army's crossing at Oppenheim on March 22 employed over 400 tanks, virtually all of them Shermans. The operational readiness rate for those tanks exceeded 90%, a figure that would have been impossible without the maintenance innovations that had been spreading through the armoured force since August. Mackenzie rotated back to the United States in April 1945, shortly before Germany's surrender. He received no decoration for the engine removal modification. There was no formal commendation. His efficiency report noted that he had demonstrated exceptional technical proficiency and leadership of maintenance personnel, but it made no specific mention of the procedure that had revolutionized Sherman maintenance. He mustered out in November 1945 with the rank of technical sergeant and returned to Pennsylvania. He reopened his automotive repair shop and spent the next 40 years fixing civilian vehicles. When local veterans groups asked him about his war service, he'd mentioned that he'd been a tank mechanic with 2nd Armored Division, worked on a lot of engines, did his job. He never talked about changing maintenance procedures or affecting operational readiness rates. The rear access engine removal method became standard practice in post-war American tank design. When the Army began development of the M46 Patton tank in 1946, the specifications explicitly required that the engine be accessible for removal without removing the turret or major hull components. The M48 Patton, which entered service in 1952, could have its engine removed in under 10 hours using procedures that were direct descendants of Mackenzie's innovation. Modern main battle tanks, the M1 Abrams and its successors, continue this design philosophy. The Abrams uses a modular power pack, engine and transmission integrated into a single unit that can be removed and replaced in under 2 hours by a trained crew using specialized equipment. That 2-hour replacement time didn't emerge from a vacuum. It's the culmination of lessons learned, starting in Normandy in 1944, when mechanics figured out that the official way of doing things wasn't always the best way. The broader lesson that Mackenzie's innovation illustrated was one that military organizations have struggled with throughout history. Technical manuals and official procedures are written by engineers and bureaucrats who understand systems in the abstract, but who often miss how those systems function under actual field conditions. The people who really know how to make things work are the ones doing the work, the mechanics and technicians who see the problems firsthand and who have to live with the consequences of inefficiency. Sometimes, the most important innovations come from the bottom up, from people who aren't supposed to be innovating at all. They're just supposed to be following the manual and doing their jobs. But when following the manual means watching people die or watching missions fail, someone eventually asks the dangerous question, what if we did it differently? Mackenzie asked that question in August 1944. Thousands of tank crews benefited from his answer. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.